In this video, we're going to be talking about how we can use symmetry to help us draw graphs of equations. So to start with, symmetry, basically there's going to be three types that will help us with graphing. The first type is a graph that is symmetric with respect to the x-axis. And that is, so an example of that would be something that looks like this, for instance. And as you can see, the way I'm graphing it, basically you need that if you knew you had some point x comma y on this graph, you know that you should always be able to flip that and get the negative, put a negative on the y, and you would still be on the graph. Okay? And so in other words, this helps you in graphing because you can do a mirror image of it basically. Do one half of it and then draw the other half to mirror it. Similarly, we can do this about the y-axis as well. Graph it being symmetric about the y-axis, well, we've seen several of these already. Let's look at something like a parabola. Why is a parabola? Well, if it's centered at the y-axis, as you can see, it's symmetric in that it sort of has a mirror image about the y-axis. Namely, if I had a point x, y here, I would expect that negative x comma y would also be a point, right? This would be negative x, this is x. Okay. Finally, there's a third type of symmetry, which is symmetric with respect to the origin. This one's a little harder to see. This is sort of almost looks like a rotational kind of symmetry. Namely, if you had something like this, for instance, symmetric about the origin would mean that it sort of has a mirror image like this. Namely, if you were to rotate 180 degrees, it would give you that. Why is this? Well, this symmetry, symmetric about the origin, says that if you have a point x, y, that means this would be x, that would be y. And then you consider the point negative y, negative x, that should also be on there as well. Okay. So for example, let's sketch the graph of y equals absolute value of x and see if it has any symmetry. First off, you should ask yourself, what are the intercepts? So let's check the intercepts. The only intercept here is if y is 0, x must be 0, and 0 and x and y, yeah, must be, and if x were 0, y would have to be 0. So there's only one intercept, and it's at the origin itself. So let's look at points about the origin. I'm going to pick several things. So here, -3, -2, -1, 0, 1, 2, and 3. Let's go 1 point extra. It'll be pretty clear with the first 5 that I usually use, but we'll go ahead and use 7 this time. So absolute value of -3 is 3, absolute value of -2 is 2, absolute value of -1 is 1, absolute value of 0 is 0, absolute value of 1 is 1, of 2 is 2, and of 3 is 3. If we go through and we plot these points, what we see is, so 1, 2, 3, 1. By the way, you should always try to draw your graph. Once you sort of know what your graph is going to look like, that's when you should sketch your axes, because then it gives you an idea of how far to draw them and such. 1, 2, 3, 4. I've tried to be good about that, but... Alright, so we have -3, comma 3. So there, -2, comma 2, -1, comma 1, 0, 1, comma 1, 2, comma 2, 3, comma 3. So it looks roughly like that. So it's sort of an infinite V. Does it have any symmetry? Well, we can see here that since absolute value of negative x is the same thing as the absolute value of any x, so no matter what x is, we actually see that, and based on this, we can see that it has y-axis symmetry. Well, this right here gives us an idea of how to check it. We know, kind of the flip side, we know we can use symmetry to sketch a graph by first testing the equation for symmetry algebraically. But how do we test? Well, the last example gave us a hint. Here's how we'll test. So if we can replace y with negative y, and this yields an equivalent equation, then the graph of the equation is symmetric with respect to the x-axis. If replacing x with negative x yields an equivalent equation, then the graph of the equation is symmetric with respect to the y-axis. Finally, if replacing both x with negative x and y with negative y at the same time yields an equivalent equation, then the graph of the equation is symmetric with respect to the origin. For example, let's try testing y equal 2x cubed for symmetry with respect to both axes and the origin. So let's go through and do the test for all three types of symmetry. Doing that, what do we test for? Well, here we want to know if replacing with negative y will give the same equation, y equal 2. So, yeah, so negative y, does that still equal 2x cubed? It's pretty clear that it doesn't, namely this equation and that equation are not the same. You could solve for y to see y, but clearly not the same equations, so no. Similarly, for the y-axis, we replace x with negative x, so we have y equal 2 times negative x cubed. Well, negative x times negative x times negative x preserves the negative, and so we have y equals negative 2x cubed, which we know is not the same thing, so no. But what if we do origin? If we look at negative 1, sorry, I don't know what's happening with that. If we replace negative y with negative 2 with and x with negative x all at the same time, here, the negative will go through. We have negative y equals negative 2x cubed. And look at that. The negatives actually cancel with each other. And so we actually do get the same. So yes, it does actually have y-axis symmetry, origin symmetry. And now it's time for you to work an example. So go ahead and test y squared equals 6 minus x for symmetry with respect to both axes and the origin. On the count of 3, I'll reveal the answer. 1, 2, 3. So as you see here, there's no y-axis or origin symmetry, but there is x-axis symmetry. All right, and now onto this example. Let's use symmetry to sketch the graph of x minus y squared equals 1. So here, this one's going to be a little bit different. Let's go through and first isolate. Well, first let's test for symmetry. So, testing for symmetry. What do we have? So symmetry test. We have what? So for x-axis, y-axis, and origin. X-axis symmetry, we replace y with negative y. We have x equal x minus negative y. Negative y squared equals 1. That is x minus, the negative times negative is a positive, so y squared equals 1. So yes, it's the same. Y-axis symmetry, if we do negative x minus y squared equal 1, we get negative x minus y squared equals 1, so no. And finally, origin symmetry, we have, for the origin symmetry, we do negative x minus negative y squared equal 1. Negative negative is a positive, so we get negative x minus y squared equals 1, and again we see no. All right, so it has x-axis symmetry. Well, that gives us an idea. Let's go ahead and look at the intercepts as well. Seps. So for the intercepts, we have the y-intercept is going to be when y is when x is 0. So that's 0 minus y squared equals 1. Here, in other words, you want to know y squared equals -1, and that does not, there's no solution to that because we have to take a square root of a negative number. And then if we look at the x-intercept, what would we have? For the x-intercept, we have that y is 0, so we have x minus 0 squared equals 1, so x equals 1. All right, and that gives us an idea. So what do we know? We know this has x-axis symmetry and we have an x-intercept. Let's start drawing out what we have so far. So we have an x-intercept at 1. So we have an x-intercept at 1, x equal 1. That is 1, 0. And we know this has x-axis symmetry. In other words, whichever side of this we do, we know that this side would get a mirror image down here and vice versa. So all we really need to do is we can use the point plotting method to pick values up here and then just reflect them down. That's how symmetry helps us. Using the point plotting method, we go ahead and we say, okay, well, let's solve out for x in terms of y. So if we choose x equal to 1 minus y, 1 plus y squared, we have, and now what we're really doing is we're thinking of x as dependent on y. So let's pick y values. Picking y values, we have 1, 2, and yeah, let's even go up to 3. When we do that, we get 1 plus 1, which is 1. 1 plus 4 is 5. 1 plus 9 is 10. So in other words, 1, 2, 3, 4, 5. I can't go all the way out to 10. But here we see that when 1 at y equals 1, x is 2. Sorry, I can't do math apparently. 2. So x is 2 when y is 1. When y is 2, x is 5. And so, and then 10, right? And so if I try to connect the points, it looks something like that. Well, understanding the symmetry, I then say, oh, well then that should have gotten reflected down, and that should have gotten reflected down. So I can do that. So that's how symmetry helps you graph. Now it's time for you to work an example, so go ahead and use symmetry to sketch the graph of y equals x squared minus 4. On the count of 3, I'll reveal the solution. 1, 2, 3. So as we see here, I went ahead and tested for symmetry. I see that it has y-axis symmetry. That means I only need to graph 1/2, and then I could just flip it. Intercepts, we got 0, -4 for our y-intercept, 2, 0, -2, 0 for our x-intercept. Here, I made a mistake and did all the points in between, but I really only need to do a couple over here. So picking 1 gives me -3, 3 gives me 5. That helps shore up my graph. I graph this side, and then I use symmetry to flip the graph and graph that side. For more practice in using symmetry to help you graph, look at page 20 of the textbook and work numbers 33 through 56. In our next video, we'll finish up talking about basic graphing with talking about circles.